we shall discuss resonance spectroscopy. It mainly deals with nuclear magnetic resonance and electron spin resonance. Resonance spectroscopy is a powerful technique that uses the magnetic properties of atomic nuclei to study the molecular structure, dynamics, and reactions. NMR spectroscopy is one of the most important methods to identify molecular structures, particularly organic compounds. When these nuclei are placed in a strong external magnetic field, they can absorb radio frequency radiation at specific frequencies, causing them to resonate. The resulting spectrum provides detailed information about the structure, dynamics, and chemical environment of molecules. Magnetic resonance imaging, abbreviated as MRI, is a medical imaging technique that is based on the principles of NMR. And in this unit, we are going to cover all the topics. First, we shall discuss the introduction about NMR spectroscopy. We shall discuss about nuclear magnetic resonance spectroscopy, popularly known as NMR spectroscopy. NMR is a versatile tool in predicting the presence of a particular nuclei in a compound. However, some other techniques are also available to know the presence of a particular nuclei in a particular atom of a compound. But NMR is highly an expensive instrument. The reason why NMR is advantageous with respect to of its cost is the utilization in finding the chemical environment of a molecule. The advantage of NMR is the chemical shift and spin-spin coupling, so that it will help us to know about not only the nature of the nuclei present in the compound, but also the chemical environment of a particular nuclei which is surrounding. The following ideas are the basics of NMR spectroscopy. Every spinning particle, like electron or proton or a neutron, possesses the magnetic moment as a result of the spinning particle. The magnetic moment is generated by a particular particle. The angular momentum is developed further rotating the molecule. For a nuclei to be an NMR active, it should be a magnetic nuclei. A non-magnetic nuclei cannot give us an NMR spectrum. We know that a nucleus consists of a proton and a neutron. Proton has a mass and a positive charge. The neutron has a mass and has no charge. The total spin of the nuclei is the sum of the spin of the proton and the spin of the neutron. For example, take an example of hydrogen, which is represented as 1H. Its atomic number is 1. It corresponds to 1 proton, that is, hydrogen nuclei consists of 1 proton and 0 neutron. So the total spin of this nucleus is the spin of the proton. The total spin of hydrogen nucleus is a spin half integral or half integral spin. Now let us take another atom, carbon 12. It consists of 6 protons and 6 neutrons. The symbol is given like this. So we have carbon 12, 6. The total spin of this nuclei is 0. That is the net spin of the hydrogen nuclei. The net spin of the carbon nuclei is 0. So there's a mistake here. It is not hydrogen, it is carbon. Now let us take C13, which consists of 6 protons and 7 neutrons. As the total spin of this nuclei is 1/2, that is half integral spin. So for carbon 12, I equals 0. For carbon 13, I equals 1/2. Now take an example of boron 10. It consists of 5 protons and 5 neutrons. The symbol is given like this. And the total spin I equals 1 here. So we have three different types of spin of nuclei. Nuclei having half integral value, nuclei having zero spin, and nuclei having integral value. That is I equals 1 by 2. This is one type. 0, this is another type. Then I equals 1, 2, 3 integer. This is another type. So totally we have three different types of spin. If I equals 0, it cannot give NMR spectra. Nuclei having zero spin are NMR inactive. Whereas nuclei having some spin, the total magnetic moment is half integral or integral, then they are NMR active compounds. So we have three classifications. One is a non-magnetic nuclei in which both the proton and neutron is even. For example, carbon 12 having 6 protons and 6 neutrons, both are even. Oxygen 16, 8 protons and 8 neutrons, both are even. Helium 24, 12 protons and 12 neutrons, both are even. And hence, when both the protons and neutrons are even, they possess zero spin, and this nuclei has zero spin. So they are non-magnetic nuclei. There is no net magnetic moment value, and hence they are NMR inactive. In the second case, hydrogen 2, deuterium, nitrogen 14, boron 10. Here, the charge is odd, but the mass number is even. Mostly isotopes. The isotope of hydrogen, deuterium, which consists of 1 proton and 1 neutron. In boron 10, which consists of 5 protons and 5 neutrons, but the mass number is even number, that is 10. So in all these cases, deuterium, nitrogen 14, boron 10, and they have integral spin. So these are magnetically active nuclei, NMR active. In the third case, hydrogen nuclei, nitrogen 15, the mass number is odd. They have half integral spin. They are NMR active. So a nucleus with both a proton and neutron having even charges, they cannot give us NMR spectra. NMR spectroscopy is an essential tool used to find out the different types of structures of organic molecules. It can tell us the number of hydrogen atoms in a molecule which are present there and their related positions in the carbon chain. It is based on the property of magnetization. That is, conductor is linked with a change in magnetic field will produce EMF and gives electricity. And spins of protons and neutrons which produce magnetic field. Protons and neutrons have spins just like electrons. Any spinning of proton will generate magnetic field, and the magnetic field of adjacent protons will cancel with each other as they spin in the opposite direction. Whereas in the case of neutrons, it has one upward quark, which is represented as plus 2e by 3, and two downward quarks. For downward quarks, the formula is minus e by 3, and will have dipole moment. Though it is a chargeless particle, it will produce magnetic field while it is spinning, because it possesses both positively and negatively charged quarks. When it spins, the nucleus will act as dipoles. So this is the pictorial representation of a subatomic particle inside the proton and a neutron. So we have two upward quarks and one downward quark in proton. So put together that will give us 2e by 3 plus 2e by 3 minus e by 3, that will give us plus e. Whereas in neutron, we have one upward quark and two downward quarks. So adding all those things, 2e divided by 3 minus e by 3 minus e by 3, which will give us 0. So it's a chargeless particle. Even number of protons and even number of neutrons in carbon 12 will spin clockwise and anti-clockwise direction will cancel with each other, even it is kept in the magnetic field as shown in the figure. So we have carbon 12, number of protons are 6 and number of neutrons also 6, and we have the mass number is 12, and 6 atoms they will have a spin up, and 6 atoms they will have spin down, that is anti-clockwise and clockwise direction, anti-clockwise and clockwise direction. When it is kept inside the magnetic field, both will cancel with each other. Hence, this type of nuclei will not exhibit any type of signal in NMR spectroscopy. Any nucleus having even number of protons and even number of neutrons, then its spin quantum number is 0, and it is inactive to NMR spectroscopy. Its angular momentum is given by P equals I cross, which is equal to I H bar, which is equal to I H divided by 2 pi. Here I equals 0. There are some nuclei having odd number of protons and odd number of neutrons will be active towards NMR spectroscopy. So number of protons will not be equal to number of neutrons. That will give us always NMR active. For NMR active, number of protons should not be equal to number of neutrons. And this is the table that will bring us what are the elements will be NMR active and NMR inactive. Suppose if number of protons are even, the number of neutrons also even, then the spin I, which is equal to 0, that is NMR inactive. For example, carbon 12 and oxygen 16. If the number of protons is odd, number of neutrons is odd, then we have I equals 1. Then number of protons is even, number of neutrons is odd, then I equals 1 by 2 plus or plus 3 by 2 goes on. Then number of protons is odd, number of neutrons is even, then again we'll have I equals plus 1 by 2 plus 3 by 2. For example, nitrogen 15. And we have the unique one, which is the protons. The number of proton is 1 and there is no neutron at all. This will have a spin 1 by 2. Example is nothing but hydrogen nucleus. One of the most important properties of a nucleus is its spin, which is represented in terms of I, or intrinsic spin angular momentum, IH. This gives rise to a magnetic moment to the nucleus. The following rules are useful in determining the values of nuclear spin I. If a mass number A is odd and the atomic number Z is even, then I is half integer, where X is the element and A is the mass number and Z is the atomic number. Examples are hydrogen 1, carbon 13, 6, nitrogen 15, 7, and so on. If A and Z are both even, then I is 0. Examples are helium 4, 2, carbon 12, 6, oxygen 16, 8, and so on. If A is even and Z is odd, then I is integer. Examples are given as like this. Now the main topic, the interaction between spin and the magnetic field. When these nuclei are placed in a strong external magnetic field, they can absorb radio frequency radiation at specific frequencies, causing them to resonate. In general, a charged particle spinning about an axis constitutes a circular electric current, which in turn produces a magnetic dipole. In other words, the spinning particle behaves as a tiny bar magnet placed along the spin axis. The size of the dipole, that is the strength of the magnet for a point charge, is expressed as mu equals q divided by 2m times I, which is equal to q under root of I into I plus 1 divided by 2m h divided by 2 pi. So which is equal to qh divided by 4 pi m root of I into I plus 1. And the dipole moment is measured in terms of ampere meter square, where Q and M are the charge and mass of the particles respectively. The magnetic moment is here expressed in the appropriate fundamental SI units, ampere square meter. When we remove the friction that electrons and nuclei are point charges, equation 4.1 is modified with the inclusion of numerical factor capital G is given as. So we'll have to include this capital G, and this capital G is the Lagrange splitting factor for nucleons. So mu equals G QH divided by 4 pi m times root of I into I plus 1. And for electron, this capital G is replaced by small g, so which is nothing but Lagrange splitting factor for electrons. Its value depends on the quantum state of the electron, may be calculated from cap L, S and J quantum numbers. Nuclear G factors, on the other hand, cannot be calculated in advance and are obtainable only experimentally. For electrons, equation 4.2 is usually written as. So instead of this one, instead of this, we can substitute beta. So mu equals minus G. So instead of capital G, we have written small g. This is for the electron. And for the minus sign, this is for the electron. So while we have introduced minus sign, and remaining factor can be written as beta. That is beta equals QH divided by 4 pi m. It's a positive constant called the Bohr magneton. Spinning the values of electronic charge 1.6 10 to the power minus 19 coulomb and mass of the electron 9.11 10 to the power minus 31 kg. In this expression, we can obtain beta equals. So substituting the respective values, beta becomes 9.273 in 10 to the power minus 34 ampere meter square. So the value of Bohr magneton is given by this expression. Nuclear dipoles, on the other hand, are conveniently expressed in terms of a nuclear magneton Bn, which is defined in terms of mass and charge of the proton. So your Bn, which is nothing but Bohr magneton for the proton, for the nucleon. So which is equal to EH divided by 4 mp pi, which is equal to 5.050 10 to the power minus 27 ampere meter square. Thus, for a nucleus of mass m and charge Pe, where P is the number of protons, we would write it using equation 4.2. So this is equation 4.2. We can write as instead of Q, you substitute Pe. So all the other terms are simple. They are similar. So we have, and substitute this one, Mp Bn, which is equal to EH by 4 pi. We will have G MPP divided by capital M Bn times root of I into I plus 1. So here mu equals G beta n root of I into I plus 1 ampere meter square, where Mp is the proton mass and the factor G is the characteristics of each nucleus. So this must be capital G. So there's a mistake here. This must be capital G. These are characteristics of each nucleus. This factor has values up to about 6 and is positive for nearly all known nuclei. Thus, the analogous of equation 4.5 and 4.6 define the equivalent spin dipole for any spinning particle. The dipole will plainly have components along a reference direction governed by Iz values. So mu Z, the dipole moment for the electron is given by this expression. The dipole moment for the nuclei is represented by this expression. So equation 4.7 shows that mu and Iz have the same sign, the point in the same direction for the many nuclei, which have positive G values. So three mu values for the system are represented by the arrows in figure A, in which conventionally the lines of force inside the magnet are drawn with an arrow pointing to the north pole. So when you are going to apply the magnetic field, and this will split into +1 and -1. So we have 0, no field, and the moment when you are going to apply, so this will become +1 and -1. And when you are going to keep any substance inside the magnetic field, so there will be a split, and we have +1 is in this direction, same direction, and -1 is lies in the opposite direction. So look at here, minus sign, -1, it is in the opposite direction. If you imagine the applied magnetic field to be produced by a horseshoe magnet and apply the same convention, it is clear that the lines of force external to the magnet will be shown pointing from the north pole to south pole, and if you require these to be in the positive z direction, we arrive the configuration given in figure B. Thus, we see that the state IZ equals -1 represents a nucleus dipole opposed to the magnetic field. This is not nuclear. This is, okay, nucleus dipole opposed to the magnetic field, that is of high energy, while IZ equal to +1 is in the same direction as the applied field, and this will have low energy. The state IZ equals 0 has no net dipole moment along the field direction and is therefore unchanged in energy whether the field is applied or not. So this is shown in figure C. Of course, if a nuclear G factor is negative, the nucleus capital G factor is negative, mu has a sign opposite from IZ, and the order of labeling the energy levels of figure C will be reversed. Similarly, the two energy levels are allowed for an electron in a magnetic field. The lower will be associated with the IZ equal to -1/2, the upper with I is equal to +1/2. The extent of interaction between a magnetic dipole and the field of strength B applied along the z-axis is equal to the product of these two, mu z and bz. Thus, the separation between the neighboring energy levels, that is IZ differs by unity, is given by del E, which is equal to EA minus IZ -1. So lower level to the immediately first upper level. So expression for EA is given by this, and the expression for IZ minus IZ -1 is given by this. So multiplying this by IZ, multiplying this by -1, that becomes +1, and first term and second term will get cancelled. We have the remaining term will be G beta n Bz, where B is the expression in Tesla. In terms of Hertz, and this is the expression, and you are going to divide both the sides by H, so that will give us in terms of Hertz, where the modular sign implies that positive differences only should be considered. A transition of electron or nuclear spins between energy levels may be associated with the emission or absorption of energy in the form of radiation at the frequency of equation 4.10. Further, since the frequency is proportional to the applied field, we can arrange to study spin spectra in any region of the electromagnetic spectrum merely by choosing an appropriate field. However, for practical reasons, the fields used are normally of the order of 1 to 5 Tesla for nuclei and 0.3 Tesla for electrons. For example, for nuclei, using beta n equals the Bohr magneton of nuclei, which is equal to 5.05 into 10 power minus 27 amperemeter square, choosing the specific value Bz, which is equal to 2.3487 Tesla, and the large G factor is nothing but 5.585. So substituting this in this expression, we can get del E by H, which is equal to 100 megahertz. So 100 into 10 power 6 hertz. So 100 megahertz. We see that the appropriate frequency for photons is obtained as 100 megahertz, which falls in the short wave radio frequency region. At this frequency, the proton sufficiently resonates and the resonance absorption of radiation takes place at this frequency. Hence, normally the proton magnetic resonance spectroscopy is studied 100 MHz frequency ranges, that is radio frequency. Suppose the same thing is for electrons, then the Bohr magneton of the electron is given as 9.273 × 10⁻24 ampere meter square, and let us assume G equals 2 and magnetic field B Z equals 0.34 Tesla. Substituting this expression, we have 9500 MHz. Thus, the electron spin spectra fall at a considerably higher frequency, which is on the long wavelength edge of the microwave region. But for an electron, this value changes from 9500 MHz, that is in the microwave frequency. In fact, many nuclear magnetic resonance spectrometers operate at just this frequency, which is why we choose such a precise value of B for this calculation. All other nuclei except tritium have smaller G factors, and their spectra fall between 1 and 100 MHz for the same applied field. Because of this difference, techniques of nuclear and electronic spin spectroscopy differ considerably. Resonance condition. When a nucleus of magnetic moment mu is placed in the magnetic field B, the interaction energy is given by E equals minus mu dot B naught, so minus mu B cos theta, which is equal to minus mu B naught ml divided by I. Since m can take 2i plus 1 values, so we have 2i plus 1 equally spaced energy levels. The energy separation between two adjacent levels is given by del E equals mu B naught del ml divided by I, which is given by this expression. So we have Gn mu n B naught. The basis of NMR experiment is to induce a transition from a lower level to the next higher level. If nu is the frequency of the electromagnetic radiation that induces transitions between adjacent energy levels, then the Bohr's frequency condition is given by h nu equals mu B naught divided by I, which is equal to mu Gn mu n min B naught, and this is the resonance condition. For spin-off system, we are going to apply the magnetic field. Then we'll have two states. One corresponds to plus of, another corresponds to minus of. So corresponding energies will be minus B mu naught and mu B naught. And the resonance condition is nothing but h nu equals 2 mu B naught. So these are represented in the following figure. When you are going to have mu equals 2.79268, and one can find out a new value, which is given as 42.5772 into 10 power 6 B naught. So when you are going to apply magnetic field, the levels are split. One is plus half and another one is minus half. So the energy levels of a spin-off system in the external magnetic field. Now let us go to the next topic, population of energy levels. We know that the nuclear or electronic magnetic moments will line themselves with the external magnetic field so that they occupy the lowest energy state. However, if we take immediately to refer a period of some seconds, then spin magnetic moments do immediately orient themselves in the magnetic field, although they do not all occupy the lowest available energy state. This is an example consequence of thermal motion and the Boltzmann distribution. And we know that the spin energy levels are split in an applied field, where the energy separation is given by del E. Let us confine our attention to particles with spin, having just two energy levels. For simplicity, however, they can be easily extended to cover the general case. The classical theory states that at a temperature T Kelvin, the ratio of the populations of such level can be given by n upper by n lower, which is equal to e power minus del E divided by kT, where K is the Boltzmann constant. Thus, at all temperatures above absolute zero, the upper level will always be populated to some extent. Although for large del E, the population may be insignificant. In the case of nuclear and electronic spins, however, del E is extremely small. So del E nuclei is around 7 in 10 power minus 26 joules with B equals to 0.3487 Tesla, and del E electrons, so this is not AE, this is del E. So del E electrons, which is around 6 in 10 power minus 24 joules with B equals 0.34 Tesla. And since K equals 1.38 10 power minus 23 JK power minus 1, we have at room temperature, that is T equals 300 Kelvin. The ratio, so this is not radion, this is ratio. Ratio of population is given by N upper by N lower, which is around e power minus 7 in 10 power minus 26 divided by 4.2 10 power minus 21, which is approximately equal to this value. So using the expansion, then we have 1 minus 1 in 10 power minus 5. This is for the nuclei. Correspondingly, we can calculate for the electron. So which is given as 1 minus 1 10 power minus 3 for electrons. In both the cases, the ratio is very nearly equal to unity, and we see that the spins are almost equally distributed between the two, or in general 2i plus 1 energy levels. The next title is Larmor precession. Consider an example of a proton in a hydrogen nuclei, and it spins in the clockwise direction, and its imaginary axis lies upward. Due to spin, it creates a magnetic field. The spinning nucleus is subjected to an external magnetic field in the NMR spectroscopy. Hence, the external magnetic field will disturb the internal magnetic field produced by the spinning of the nucleus. The symmetry of the spinning nucleus will be disturbed. Hence, it will start rotating as precessional motion. This type of precession is known as Larmor precession. So there's a mistake here. It is precession. Here, all the rotation axes are quantized. Thus, this hydrogen nucleus will rotate only in the quantized state only. We can have number of orientations, that is number of allowed orientations. For example, I equals 1 by 2, we have 2i plus 1, 2 multiplied by 1 by 2 plus 1, that is equal to 2. So we have only 2 orientations whenever it is subject to an external magnetic field. So we are going to apply magnetic field, there will be a split. So one is plus half and another is minus half. Minus half will be a lower energy and plus half will be a higher energy. Two spin states, proton will be oriented along or against the external field. The orientation which is aligned along the external magnetic field will have lower energies, which is a stable one, and opposite orientation will have high energies, which is unstable one. Let us take an example of ethyl alcohol and examine for the NMR signal. Let us keep it in a beaker. So we are going to keep ethyl alcohol. So the ethyl alcohol in a beaker, and you are going to keep a magnetic field, and we are going to observe NMR signal. It is carbon 12, which is I equal to 0, which is nothing but even number of protons and even number of neutrons. And this will not respond to NMR, we know already. And similarly, oxygen 12, again I equals 0, and this will not also respond to NMR signal. Whenever this solution is subject to an external magnetic field, the carbon and hydrogen will not give any signal, but we will get signals only from the protons, the presence of the hydrogen. If the solution is kept under the magnetic field, it will produce 3 different signals, since the arrangements and the environment of 3 different protons are different. And we have the formula for ethyl alcohol, CH3, CH2, OH. So we have 3 signals. and these signals are different orientation of the protons, that is for the hydrogen atom. Now let us consider the 8 atoms of ethyl alcohol. Out of 8, let us assume that 6 are aligned along B and 2 are in the opposite to B. So let us assume that 6 atoms are aligned like this. So we have 6 atoms are aligned along with B and 2 atoms are aligned against B. Let us assume the upper protons will have lower energies and the lower protons will have higher energies. So upper protons will have lower energies and the lower protons will have higher energies. Lower means more stable. See, the lower means they have more stable, and high energy implies less stable. So the net magnetic moment will be oriented along B as it has more number of nucleons in the upper level. So we have more population in the low energy area and less population in the high energy area. This type of unequal distribution is known as Boltzmann distribution. While applying magnetic field, all the nuclei will precess, and this will have some frequency which is known as Larmor frequency, which is directly proportional to the applied magnetic field. So you have del E is directly proportional to the external magnetic field beta B naught h bar, h divided by 2 pi, and this is equal to some constant. This constant is known as ferromagnetic ratio, and this is defined as magnetic moment divided by angular momentum. And this ferromagnetic ratio is different for different nuclei, and it's a constant value for a particular nuclei. Now we are going to send some radio frequency signals to the sample now. So we are going to send some radio frequency signals. Whenever the frequency of the precession nuclei matches with the frequency of the electromagnetic wave, then we will have resonance. It implies that the electromagnetic wave is absorbed by the nuclei and the nuclei will have more precession. It implies that they are precessing now in resonance. Hence, some energy will be absorbed by the nuclei and this will have more energy. Since they have more energy, they can come to the higher energy states. Since they have more energy, they can come to the higher energy states. So this will have already low energy, and 2 of the atoms, they can come down to the higher energy states. Hence some energy will be absorbed by the nuclei and this will have more energy. Since they have more energy, they can come to the high energy state. Let us assume that 2 nuclei flip down as shown in the figure. Then the magnetic flux linked with the conductor. So this is the magnetic flux linked with the conductor. So this conductor is there. So there will be a change in magnetic field. So magnetic field linked with the conductor suddenly changes. So automatically EMF will be generated in the coil, and this signal will be recorded by the NMR meter and analyzed. Now we have only 4 atoms in the lower energy level and 4 atoms in the higher energy level. We know that any molecule staying in the higher energy states are highly unstable. The arrangements of all other nuclei present in the solution are known as lattice, and they have their own oscillating frequencies. All the atoms are placed in the lattice. These vibrations generally will be more in liquids and gases than the solids. So they have their own frequencies. Whenever the frequencies of the vibrating nuclei in the higher energy states match with the frequencies of the vibration of the lattice, then the energy of the nuclei will be transferred to the lattice. Hence the nuclei will give up some energies to the lattice. It can be either rotational or translation energy or thermal energy. It is just that those nuclei again will flip into the lesser energy states. So the population in the lower energy states will be higher than the number of nuclei in the higher energy states. This type of relaxation from high energy states to the lower energy states is known as spin relaxation time. And this relaxation time is less in liquids than in solids. In earlier example of considering 6 protons in the lower energy states, which act as tiny magnets, the resultant magnetic field, which is nothing but longitudinal as shown in the upward. So we have the resultant magnetic field is nothing but longitudinal magnetic field, that is along the external field. So there will be a transfer of nuclei continuously from low energy states to high energy states and vice versa, resulting in a change in longitudinal magnetic field. So what will happen? And the strength of the longitudinal magnetic field will appear, and after some time this will disappear. So appear and disappear will happen for the longitudinal magnetic field, and this change in magnetic field linked with the coil automatically will have some signals. This continuous change in fluctuating magnetic field enough to create signals as in the case of dipoles. This change in magnetic field linked with the coil produces an EMF and gives us signals. This type of relaxation is known as spin lattice relaxation. Now let us consider again 4 nuclei in the lower energy state and 4 nuclei in the higher energy state. There is no longitudinal net magnetic field. Now the electromagnetic wave falls on the system. Then all the nuclei will come to one side, as shown in the figure. So this is the normal one. The moment when you are going to send the electromagnetic field, all the 4 electrons, they will come this side, see, on one side. And here also we have on one side. All the 4 electrons will come on one side. There occurs the resultant transverse magnetic field. Now what will happen? The resultant transverse magnetic field will appear. See, we have the resultant transverse magnetic field. Earlier we had the resultant longitudinal magnetic field. Now we have the resultant transverse magnetic field. However, it will last for only few seconds. Again it will come to its original position as nearby electrons will repel each other. So now electrons are very close, they will repel each other, again they will come to its original position. If the repulsive force of the nuclei is stronger, it will lose its symmetry and it will come to its original position. Eventually, the transverse magnetic field will disappear. Again, they will be aligned in one direction, where the transverse magnetic field will disappear. Again, they will be aligned in one direction, and the transverse magnetic field, this continuous change in magnetic flux linked with the conductor produces EMF, and it gives out the signal which will be recorded by the NMR spectrometer. This type of spin-spin coupling and relaxation is known as spin-spin relaxation, that is T2. T1, which I have already studied, is nothing but spin lattice relaxation, and T2 is nothing but spin-spin relaxation time. Thus, these relaxation process will give varying magnetic field and produce signals which will be recorded in the spectrometer. Thus, in order to obtain signals, we change the frequency of electromagnetic waves by keeping the magnetic field as constant, or we can change the magnetic field by fixing up the radio frequency constant. Hence, there are 2 factors influencing signals. One is magnetic field, then another one is electromagnetic wave. Frequency of the electromagnetic wave. We know that the dipole moment of a spinning nucleus is given by mu equals G beta n. G is the Lambda factor, and beta n root of I into I plus 1 ampere meter square. Beta n is the Bohr magnet of the nucleus, and that according to quantum laws, the vector represented by mu can be oriented in particular directions only, so that its components are integral or half integral in the reference direction. The corollary to this is that since root of I into I plus 1 cannot be integral or half integral, if I is integral or half integral. the vector arrow can never be exactly in the field direction. For a nucleus, with spin I equals 1 by 2, we have the dipole moment mu equals g beta n root of 3 by 2. And the component of a dipole moment mu z equal to plus or minus 1 by 2 g beta n. Thus, whichever energy state a spinning nucleus or electron is in, it will always lie more or less across the field and will therefore be under the influence of a couple tending to turn it into the field direction. Now, the behavior of a spinning nucleus or electron can be considered analogous to that of the gyroscope running in friction-free bearings. Experiments convince us that the application of a couple to a gyroscope does not cause its axis to tilt but merely induces a precession of the axis about the direction of the couple. Essentially, the same occurs with the spinning particle and the precession, known as Larmor precession, and is sketched in figure. So this is our Larmor frequency. When you're going to, the moment when you're going to apply the magnetic field, and precession will take place, precession of the nucleus will take place. The precessional frequency, which is nothing but Larmor frequency, is given by omega equals magnetic moment divided by angular momentum times Bz. This is measured in terms of radians per second. So which is equal to mu Bz divided by 2 pi I measured in hertz. Replacing mu and I by their expressions in equations 4.16. So we have equation 4.16 and 4.14, and the corresponding frequency omega is given as g beta n root of I into I plus 1 B is divided by root of I into I plus 1 hertz divided by 2 pi multiplied by 2 pi. So we have omega equals mu B z by 2 pi I, and we have the expression for mu. You substitute mu here, we'll have this equation 4.17. And of course, when you're going to divide both sides by h, that will be recorded in terms of h. And comparing with the equation 4.10, so this is the equation 4.10. Let us see, almost they are same. We see that Larmor precession frequency is thus the frequency separation between energy levels. So this is the mechanism by which particle spins can interact with the beam of electromagnetic radiation. If the beam has the same frequency, what we call this as resonance, as that of a precessing particle, it can interact coherently with the particle and energy can be exchanged. If it is of any other frequency, there will be no interaction. This phenomenon is known as resonance. For nuclei, it is referred to as nuclear magnetic resonance, NMR, while for electrons, it is called as electron spin resonance, ESR, or sometimes we call this as electron paramagnetic resonance. Experimentally, there is a choice of two arrangements. We might either apply a fixed magnetic field to set of identical nuclei so that their Larmor frequencies can be 100 MHz. If the frequency of the radiation beam is then swept over a range including 100 MHz, resonance absorption will occur precisely. On the other hand, we could keep the nuclei in radiation at a fixed frequency of 100 MHz and sweep the applied field over a range until absorption occurs. The probability of transitions occurring from one spin state to another spin state is directly proportional to the population of the state from which the transition takes place. However, while the lower state is more populated than the upper state, example, at equilibrium in the absence of radiation, the upper transitions predominate slightly and the net absorption of energy occurs from the radiation beam. When the populations become equal, upward and downward transitions are equal. So no further absorption takes place and the system is said to be saturated. The equilibrium populations can be re-established if the system loses its absorbed energy, thus it cannot do spontaneously, but only as a result of interaction with radiation. Now the next topic is relaxation times. In nuclear magnetic resonance spectroscopy, relaxation time is the time it takes for spins to return to their equilibrium energy levels after a pulse. The relaxation times in NMR are typically between 0.1 and 10 seconds, but it can vary depending on the number of factors, including oxygen. Relaxation times are longer in the absence of oxygen. Chemical exchange. Relaxation times are shorter when there is medium to fast chemical exchange. Paramagnetism. Small amounts of paramagnetic substances in a sample speed up relaxation. NMR frequency. The rates of relaxation are strongly dependent on the NMR frequency. NMR relaxation times can be measured from NMR pulses. There are two main types of NMR relaxation times. One is spin-spin relaxation time. The loss of spin coherence in the X-ray plane. Transverse magnetization relaxation decay measured via Horn echo sequence or a solid echo decay. Then NMR relaxation times can be used to characterize fluid content, fluid type, and pore size. They can also be used to study molecular dynamics in confined polymeric systems. The last topic is double resonance. Double resonance is a spectroscopic technique that uses two electromagnetic radiation sources, often of different wavelengths, to study energy transfer and interaction between the different energy levels in the system. Yet two radio frequencies are used to manipulate and observe two distinct nuclear spins, simplifying complex spectra by removing spin-spin coupling and revealing clearer signals. It is used to simplify spectra, resolve complex interactions, and gain insights into molecular structure and dynamics. Types of double resonance. Electron nuclear double resonance. This technique uses both microwave and radio frequency radiation to study the interaction between electron spins and electron and nuclear spins in a paramagnetic species. Nuclear magnetic double resonance. This involves using two radio frequencies to decouple spins, simplifying spectra and revealing information about spin-spin coupling. Optical double resonance. This technique uses two different wavelengths of light to probe the energy levels of molecules, often in conjunction with microwave or radio frequency radiation. Two radiation sources. Double resonance experiments involve using two different types of electromagnetic radiation, such as microwave and radio frequency, or two different wavelengths of light. Energy transfer. The first radiation source is used to induce transitions between energy levels, while the second radiation source is used to probe system and to observe the effects of first radiation. Spectral simplification. By carefully controlling the two radiation sources, it's possible to simplify complex spectra and resolve interactions that would otherwise be obscured. Information extraction. Double resonance experiments provide valuable information about the molecular structure, dynamics, and interactions. Applications. Spectroscopy. Double resonance techniques are widely used in spectroscopy to study molecular structure, dynamics, and interactions. Chemistry. They are valuable tools for organic and inorganic chemists to analyze complex molecules and reactions. In physics, double resonance experiments are used to study the properties of materials and fundamental interactions. And in biology, double resonance techniques are used in structural biology to study biomolecules.